So up until now, we've only been talking about limits as we approach a point. So just make a note over here. So previously, we only talked about the limit as x approaches a of f of x. So we were talking about just a specific real number, a point that we're approaching on the x-axis. All right, so now what we want to do is talk about limits as we go to infinity. So we're calling this limits at infinity, although again, not really a great term because we don't reach infinity, but as we approach infinity. But it makes a nice way of talking about the other limits, limits of infinity, when you get a limit to be infinite versus limits at infinity when you're heading towards infinity. So we have a couple of equivalent questions because this is a very important topic, and so you see it phrased differently. So one way you might see this referred to is what happens to f of x as x approaches infinity and x approaches negative infinity? Or what happens to f of x as x increases or decreases without bound? Meaning the same thing. A lot of times graphically we talk about what is the end behavior of f of x. And in fact, if you were to see this in more of a applied circumstance, you might hear it referred to as what is the steady state behavior of a system as, say, time t goes to infinity. That's a really important topic in, say, differential equations or in really modeling of natural phenomena. Okay, and then we have the very common, what we'll see is just the mathematical expression, limit as x approaches infinity of f of x is what? And limit as x approaches negative infinity of f of x is what? Okay, so graphically what we're talking about is we're talking about what happens as we go out here and back here. So out here towards infinity and back here towards negative infinity. Okay, so we're not at all concerned what's happening in between. That doesn't really matter to us. That was something we were looking at before, but now we're only concerned about what's happening as we go far out to the right and far back to the left. Okay. Another if you remember when we had a limits of infinity, they led to vertical asymptotes. Interestingly enough, now our limits at infinity can lead us to horizontal asymptotes. All right, so let's look at that. If the limit as x approaches infinity of f of x is L, or the limit as x approaches negative infinity of f of x is L, then the line y equals L is a horizontal asymptote of the graph of f. So what this is telling us is that there is some line in the graph that the function is approaching, at least in one direction, often positive infinity or negative infinity, and possibly both. So let's take a look here on the left of a particular what a horizontal asymptote might look like. So you could have a horizontal asymptote, say, at y equals 1. So let's make that y equals 1. And as with any asymptotes, we generally dot them. All right, and what you might have is you might have a function that looks like this. Okay, so you see that we have, as x is going to infinity here, we're trying to indicate that this function in red here is getting closer and closer to the line y equals 1. Okay, or you could have something that has a horizontal asymptote at y equals 0, so it's hard to see, but I'll just try and dash the x-axis here. And So this function, maybe you have a function that looks like this. All right. And again, I'm trying to indicate that this function approaches the x-axis as you go off to negative infinity this time. Okay, so one interesting thing is how many horizontal asymptotes a function can have, the graph of a function can have. Because with vertical asymptotes, you could have any number of vertical asymptotes. None, 1, 2, 3, 4, 5, infinite. So note that with horizontal asymptotes, you can have 0, 1, or 2 horizontal asymptotes. Okay, so let's look at some examples of each. So you might have just a simple, maybe you have something like f of x equals x. This does not have any horizontal asymptotes because as you go off to infinity, positive infinity, you don't approach any sort of specific value. In fact, the function is just going to keep going off to infinity. And as you go to negative infinity, we see that the function also just keeps going to negative infinity, doesn't approach any specific value. Okay, so how about something with one horizontal asymptote? Well, we could have something like f of x equals e to the minus x. All right, and that looks like this. All right, and so here again, I'm trying to indicate that the y equals 0, the x-axis, is a horizontal asymptote because as x goes to infinity, e to the minus x approaches 0. Okay, we'll see more about that when we do the limits. All right, what about 2 horizontal asymptotes? So that's a stranger situation, but there are plenty of functions that have that. So we could have one good example is actually inverse tangent, which looks like this. And has horizontal asymptotes at y equals pi over 2 and y equals negative pi over 2. So there's an example of 2 horizontal asymptotes. Now you'll see that we can have lots of different variations on this. We can have the function approach the same horizontal asymptote going both ways or just one way, as long as the function approaches that value, that line, in one direction, it's a horizontal asymptote. It doesn't have to do it in both, and there can be different ones. Let me also make a little side note here. A function's graph can cross a horizontal asymptote. Okay, it's not going to happen all the time, but you could have a function that had, say, a horizontal asymptote here, and what the function actually does is maybe keeps going above and below it and sort of hugs it and eventually goes close to it, or eventually approaches it, or that would be sort of having it cross infinitely many times, or you might just simply have something that crosses maybe once and then comes up and approaches the horizontal asymptote. So you can never cross a vertical asymptote, but you can cross a horizontal asymptote. I don't see it a lot, but it certainly can happen. So let's take a look at two important results that we're going to use quite frequently. The first says that if R is a positive rational number and C is a real number, then, all right, so what we're looking at is the limit as x approaches infinity of some constant C over a power, a positive rational power of x. And so what's going to happen here is that as x goes to infinity, if this is a positive rational power, and the only reason we want it positive is because we don't want it to be able to flip up into the numerator as positive, but this thing is just going to keep getting bigger and go to infinity as x goes to infinity. And if it's just a constant at top, then that's a fraction that's going to get smaller and smaller and go to 0. And it actually doesn't matter if we go to negative infinity in a similar situation, because this denominator is still going to go to infinity. I mean, it might go to a positive infinity or it might go to negative infinity, depending on what the power is. And it also may not be defined. So we're saying if it is defined, we don't want to do, I'll be putting negative numbers in a root, say, an even root, and we still have a constant on top, so we still have a constant over something that's going to an infinity, and this is still going to go to 0. So those are very important. We're going to see that a lot. The other situation that we often see is with the exponential. If you remember, the exponential e to the x looks like this. All right. And what we're saying here is, as we go off to negative infinity, the value of e to the x approaches 0. And as we saw in the example above, if we talk e to the minus x, that's just flipped over the y-axis. As we go to infinity now, the function approaches 0. So those are two more limits that are very important to us.